So the lesson we're considering is of belt drives. When you look at belt drives, they're used to transmit motion from one pulley to another between parallel shafts. It can also be shafts at different angles. And the main two families we have could be the flat and V belts. You can use the dimensions provided, like center distance, the diameters of the two pulleys to calculate the total length of the belt. So that is what this is all about. And there, the most important one you need to find is the angle theta. Once you get theta, then you can proceed with the rest of the calculation. Now, in designing flat belts, we want to realize that there are always two sides. A belt drive will have the side which is tight and the side which is loose. If T1 is the tight side, then T2 is the slack or loose side. If you reach a condition where the two tensions are the same, then that belt is slipping and there is no transmission of motion taking place. So the difference between T1 and T2 is the one known as the driving tension. Now here, when you do the resolution, our focus is on this formula we have below here, which is the relationship between T1 and T2. So the ratio between the tension on the tight side and that on the loose side is given by E raised to power mu theta. The factors mu represent the coefficient of friction between the belt and the pulley. Then theta is the angle of lap, meaning you look at the angle, the belt is contacting the pulley. That is the angle of lap. In this case, let me go back to, our usual, what we're looking at. If I take us back to the, so the angle of lap is this angle shown here, from here all the way to there. The angle of contact or the angle of lap. So the bigger the angle of lap, at least the lower the chances of slipping. If the angle of lap is very small, then you expect that the belt can easily slip and we have other problems coming. Now, having known this relationship for a flat belt, and not about the power that is going to be transmitted. The power transmitted is what we have here. It's you multiply the driving tension by the velocity at which the belt drive is running. So T1 minus T2, then V comes outside the box. T1 minus T2, that's our driving tension, then V is the velocity. Then if you go back to that relationship we have there, you substitute, make T2 the subject of the formula. It simplifies to T1 outside the brackets, then 1 minus 1 over E power mu theta. And you're multiplying everything by the velocity V. Then moving on, the centrifugal tension is very important because this is when the mass of the belt has been considered. Centrifugal tension, which is Tc, is given by the product of mass and the square of the velocity, so mv squared. For maximum tension, or for maximum power to be transmitted, the condition is that T, which is the maximum possible tension, is equal to 3 times Tc. Now, T1 over T2 equals E to power mu theta. T1 is where the T is T1 minus Tc. So if you notice, this ends up like that, where you subtract the Tc and then you have E power mu theta. But the shortcut is here. The T that we were provided with, multiply take away TC, then open brackets 1 minus 1 over e power mu theta. Close the brackets, then you have the velocity. This gives you the power. Even before you can find T1, you're able to find the power directly. The rest of the processes are the same. When you're dealing with the V belt, you need the groove angle. This is the groove angle, the angle of the groove. That angle, once it has been given, then we modify. The ratio between T1 and T2 is given by e raised to power mu theta cosec beta over 2, beta over 2. So beta is the groove angle. So divided by 2. When we say cosec, we're referring to 1 over sine. Cosec beta refers to 1 over sine beta. So the formulas that we're considering are just here. If we're dealing with a V belt, then we look for the other one, which is for the transmission of power and also for the amount of tension you have on the slack side and the tight side. So here is one example that helps us to illustrate everything in one go. So this example says a flat belt of cross-section 100 by 5 millimeter manufactured from material of density 900 kg per cubic meter. The belt is used to transmit power to a pulley whose angle of lap is 150 degrees. And the coefficient of friction between the belt and the pulley is 0.25. The maximum stress in the material of the belt is not to exceed 2 newtons per square millimeter. Then the speed of the belt is 30 meters per second. We need the power, maximum power, and also the power transmitted. Suppose we're using a V belt, groove angle included is 32 degrees. So we can organize our information. The area is 5 by 100. So what we have here is the cross section of this belt, which means we have a similar situation like that, where the thickness of the belt is here, that's your 5. The width here, this is the 100 millimeters, so this is 100. How do you get the area? The area now talks about this thing here, the cross-section area. So the area, you multiply the width by the thickness, so you have 5 by 100 giving you 500 square millimeters. What about the density? The density of the belt, we already told it's 900 kg per cubic meter. So we don't need to convert anything. But when it comes to the area, we can also decide to convert it to square meters if need be, especially when we come to calculating for the other factors. But let's leave it there for now. So here, continuing, we have coefficient of friction, which is 0.25. The velocity of the belt is 30 meters per second. Mass of the belt, we're going to multiply the density by the area. Meaning this is not going to be the actual mass, it will be the mass per meter. Because if it was supposed to be the actual one, this should have been volume. But we are multiplying, we're getting the mass per unit length. So 900 multiplied by the 500 that we've been given is in millimeter squared. So how do we convert them to square meters? We just divide by 1,000 squared, then this has been converted. The other way is to convert these individually. The result will still be the same as 0.45. The angle of lap also is supposed to be in radians. So theta, which is 150 degrees, multiplied by pi over 180. The answer is 2.618 radians. With this information, we want the power transmitted. So the power transmitted, first we need T, the maximum possible potential. So T is stress multiplied by area. The stress is 2 newtons per square millimeter multiplied by the actual area, which is 500 square millimeters. The two are speaking the same language, no need to worry about the units. So 2 by 500 gives us the 1000. Then centrifugal tension, we multiply the mass per unit length by the velocity, by the square of the velocity. So 0.45 by 30 squared. The answer is 405 newtons. From there, we can now use that formula we started with. T1, open brackets 1 minus 1 over e power mu theta. So instead of having T1, this is it. It's T minus Tc. Then from there, we can now substitute. The T is 1000. Tc 405. Then E raised to power mu 0.25, the theta is 2.618. When you enter this in your calculator, the end result is this. You have 545 by 0.4803 by 30. And your power is 8573.322 watts. This is just the power transmitted. Question B was asking for the maximum power transmitted. As for the maximum power transmitted, the condition is that the T is supposed to be 3 times Tc. Meaning from there we can get Tc by making it the subject. So it will be T divided by 3. And this is what you get, 333 by 0.333. Then what about T? We're told T is 3 mv squared, there's a 3 Tc. So when we substitute and expand, this V we have here is our Vmax. When you make it the subject, this is what you get, T over 3m. So you have T, which is 1000 divided by 3m. The mass, the unit length is 0.45. And the result is 27.216 meters per second. You can ignore this. This is talking about meters per second. Just that these computers also sometimes try to have a mind of their own. Now, from finding that power, then you can also find the power after finding the velocity at which maximum power is transmitted. Let's go for the velocity there. In the velocity, we are saying power is equal to, rather finding the power, the maximum power, we'll say T, take away Tc. So open brackets, you have 1 minus 1 over e power of theta. Then Vmax outside. So here the information, we always remember to get this, the one we found. Then the rest of the information is the same, but here we also remember to put the Vmax we calculated, which is 27.216. The answer gives us 8714.567. That's our maximum power. What if it's a V-belt? With a V-belt, we just include this part. The rest is the same. Centrifugal tension is the same, and the rest. So you set T minus Tc, then we have 30 here, and then we change everything. And in that case, your answer comes out as 16.188 kilowatts or 16,188.856 watts. When the centrifugal tension hasn't been provided, the work is actually much simpler because here you just have T1 and you proceed with the rest. There's no Tc. Tc is zeroed. Yes, I think that's the one that was in the other example handled in the previous work that we did. So for now, look at the exercise. We have 5 questions. already provided with the answers. You can take your time to look at how this works out. Okay, for now, I think we'll end here. Thank you for paying attention.